because we've already done, like I said, we've already done addition in one way. We just have function notation to learn. Same as subtraction and multiplication. Division is going to be different. But before, do you remember when we had this kind of problem? We had x plus 2 plus x minus 1. Do you remember when we had this kind of problem early on? It was like y is equal to, right? Okay. So this, if this function over here, if this function over here, if we called this f of x, and we called this g of x, essentially, for addition, what we see here is f plus g of x. And that's exactly what I have here. I'd write that as f of x, right, plus g of x. That's all this function means. That's all the function notation is saying. This function notation, you're never going to try to solve for any of these variables. That's going to be intact. That's going to be essentially a guide. Function notation is a guide on what we're going to plug in and what functions we're going to combine, or we're going to divide or multiply. So you're going to leave this, and this is another form. It's function notation, but it is essentially our y value, our output. Okay? So we can think of it that way. If I kept these values, I'm just going to put them like this. If f of x is x plus 2 and g of x is x minus 1, right? F plus g of x is x plus 2 plus x minus 1. And remember when we had the polynomials like this, what do we have to do when we add? We just have to do what? Really combine like terms, right? Subtraction's different. We got to distribute. But here, we're just going to end up with these terms and combine them to get that. That's our answer. Yeah. Well, it was a review earlier on. I don't believe that they did function notation in this way. Yeah. You know what? I don't think they did the domain restriction in this way either. So that's the addition. That's why I liked it for a Friday lesson, because it is just like a step up. So you guys are commenting like maybe I can go faster through those first three, get to the new stuff. Sound good? Okay. So the same functions, if I was just doing f minus g of x, it's important to have it in the right order, because when you subtract two numbers, if you put them in a different order, you're going to get a different value. So we just have to be careful with this. But it's just going to be x plus 2 minus x minus 1. So we just got to remember, the main thing for this is we got to remember to distribute. All right. We distribute, we get down here at x plus 2 minus x plus 1. Because I distribute that to negatives. Help us change that. Oh, in this case, we get f minus g of x is equal to, the x's are gone, so it's equal to 3. Which is possible. That's fine. That'd be my answer in that case. That's based on the f of x and g of x we started with. All right, I'm just going to remind you quickly that if I have these two, it's not next level. I'm going to use these actually for this next example. So let's just use these as our f of x and g of x. If I'm multiplying, this should look a lot like FOIL, even though the terms are a higher degree. It's just going to be multiplying them. That's what that notation is mean. That's what it means. F times g of x. Okay. So let's see what we get. 2x to the third first. Outer plus 4x. Inner plus 3x squared. Last plus 6. So put in descending order, always left to right, and we got it. Right. Everyone okay with everything so far? Everything so far? Thumbs up? Thumbs up so far? Thumbs up? Good, 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 good. Okay. The divide part is the tricky part. And I want to start with two new functions that I know will work out nice and also will require you to put on your test maker's hat. Because being able to deduce what the test creator was thinking may be helpful with these. Let's see, maybe not. F of x is x plus 2. G of x is x squared plus 5x plus 6. We want to do f divided by g of x. We want to see what happens there. So let's see. We go x plus 2 over x squared plus 5x plus 6 because I'm just putting them in the form. Those at home just missed that. So we're doing division. That's what I want. Now, what's one thing we got to remember when we have fractions? We can't have what? You can't have, with a fraction, you can't have what? You can't have a 0 in the denominator, right? 4 over 0. Hey, here's 4 of my 0 cookies. That's not nice. You can't do that. 0 on the bottom doesn't make sense. 1 out of 2 cookies makes sense. I'll give you 1 of the 2 I have. If you have 0, and you're giving some 4 out of 0, it's like an IOU cookie. Those aren't good. Nobody wants that. Okay, I'm going to put some marks up here. There's a lot of like, there are like 4 different. All right, I put parentheses around the top. I hope that gives you a clue. Put on your test maker's hat. What method are we going to use to maybe change that bottom trinomial into something that will allow us to simplify this? Simplifying maybe crossing out because it's a special 1. That equals 1, so I can cross those 2 things out. That might be it. Tell your neighbor, what do you think? What are we going to do with this bottom? The denominator? We need to put it in a different form to take our next step. What do you think? Tell your neighbor. 5 seconds, real quick, real quick. So I'm hearing some things in the right direction and others not. So just hold off telling because it may be the wrong direction. I think. But was my clue for the parentheses? Does it help if I put parentheses like that too? What method, Caitlin? What are we going to do? Trinomial. The 3, 1, 2, 3. Factor that into what? Right. 2 binomials. Who knows the method we use to do that? X method. You see, if I use the X method, what multiplies to give us 6? What multiplies? That's my C value. What adds to give me 5? Adds. That's my B value. What are 2 numbers that fit there? 2 and 3, if you didn't know, you take 6 and say, what are the multiples? But I think we can see pretty quick. 2 and 3, right? So we have x plus 2, we have x plus 3. That replaces my trinomial. Do you see the logic somebody created this problem? Math problems, while you're learning math, aren't from just like outer space. Like they are created. Otherwise, our answers would all just be, you know, maybe indeterminate decimals that went on forever. It'd be harder to see that you're on the right track. We see we're on the right track because at this point, you know, this is equivalent to this. Why is that helpful? Why is that good that we have it in this form? Yeah?
You could take both the x plus 2's and like cross them out.
Yeah, because x plus 2 over x plus 2 is equal to 1. We've made it equal to 1, and when we cancel, cross it out, that term in this case is talking about we have a special 1, so we can make that. That's equal to 1. That's pretty good. But you get to this step, and you got to stop. This is where you're going to stop for a second. Stop. After you have it to the point where you're about to simplify it, stop and make sure you get all the information from this step that we need. Because what do we need to do? The restricted domain, since the denominator can equal 0, cannot. Before we simplify, we need to find what x values. Domain is x. Domain is our x values. What x values can we not have? X cannot equal what? And x cannot equal what? Tell your neighbor what you think. I'm going to write it below this. I want you to look at the denominator to tell me when do these equal 0? X can't be what? And x cannot be what? Tell your neighbor what you think. If you're confused, peek up here. If this ended up being 0, anything times 0 would give us a 0. So I want to know when that happens and when that expression is equal to 0. When will that happen? We plug in. So again, you can't have a 0 in the denominator. So I want to know, since these are two expressions like this, essentially, right? If that ends up being 0, the whole thing's 0. If that ends up being 0, the whole thing's 0. So now tell your neighbor for sure, what two x values can we not have? We're looking here. All right, let's bring it back. What x value for the left expression here on the denominator, what x value do we put in that this would become 0? -2. Can't have -2. X plus 3. What value for x do we put in so that this expression is 0? -3. We cannot have our answers be -2 or -3. That's part of your answer. That is the domain restriction. We're not saying how we're cropping the window. In this case, we're saying what x cannot be. Before we crop the squirrel, remember we did the x values. Domain is actually cropping it. Domain restriction is saying what it cannot equal. Domain restrictions often happen when we have a fraction going on because we can't have that 0 on the bottom. So this is called the domain restriction. Slightly different. Domain constraint, restriction. All right. I should put a semicolon kind of in between these. So we've done this step. We did this step right here. We found the restricted domain. Now we're going to go ahead, since we've done the restricted domain, now we're going to simplify. Atin?
When we use domain restriction, is it saying that the x-intercepts of the parabola can't be reduced to the negative?
You're trying to relate two topics that don't really fit right now. This isn't talking about your x-intercepts. These aren't x-intercepts. If I don't know what this function looks like, I don't actually know if it's a parabola or not. I don't think it's a parabola. It's Desmos you would see. But what these are talking about, this is a continuous function, right? Continuous function. Say this is what the function looks like. What this is saying is along our x-axis here, along our x-axis, at -2, it's undefined, so the x cannot equal -2. At -3, it's also undefined, so it would be like a hole in your function. That's more of what this is talking about. It's not talking about the roots, because in order to find the roots, we have to see when y is equal to 0, what's happening, and we haven't even used that kind of method at all to get to these. So it's just unrelated. I'm glad you brought it up, though, because I get to show, that's when we have a hole. They're called holes. So you'll have a function that's continuous. You can gather information from it. You get to one of our domain restraints, and it's just going to be a hole at that point. -2 and -3 are going to both have that hole going on. All right. So let's go ahead and simplify this. What can I cancel out because it's a special one? X plus 2 over, right? Because this right here, that equals 1, so we can cancel it. And then I'm going to bring it over here for our last step. Last step. So now we have f of g of x is equal to 1 over x plus 3. This is part of our answer. This is our equation answer. We need the range constraint now. Restriction. All right, now follow me with this. It's going to be y cannot equal something. I want to look at my two domain restrictions. One is going to just be undefined. The other is going to actually give you the range restriction. Think about this for a sec. If I plugged in -3 right here, what do I end up with? -3 plus 3, 1 over 0. That's undefined, right? So I already knew that because our -3 Our negative 3 creates a scenario where it's undefined because it would be a 0 below the fraction. But after we simplify it, this plus 2 isn't a component of the denominator. So now I need to look negative 2. What happens if I put negative 2 in here? Put negative 2 plus 3, 1. 1 over 1? 1 over 1? 1. Basically, you want to go in and take your domain restrictions that you found before simplifying, make sure you plug them into the final answer that you get after it's simplified. That'll give you a range restriction. Here, x or y cannot equal 1. The reason why I didn't put y cannot be undefined is because the nature of the term and status of being undefined is that it's not defined by anything. You can't equate that. It's if something, I wouldn't write y cannot be undefined because that's kind of given and obvious. It's not something we need to keep noting like that. Yes, y cannot be undefined. And you would put that for an answer for every single problem you ever did then. So here we just, before factoring, we find our x domain restrictions. We factor or get it all the way simplified. We plug in our values, and the one that gives us a numerical value, that's what our range restriction will be. Yes?
So is range restriction also like the y-axis is going out 1 and that's in there?
Yes. And if the function I had it before, if it was accurate to this and graphed it, we'd see that it would be a hole. So there is a hole, right? What did I get? What did I plug in here? It would be at negative 2. When I plug in negative 2, I get 1. So there would be a hole at negative 2, 1. Yeah. The other one, I think I want to graph this to actually talk about it, not hypothetically. So we could graph that with the table and just see really quick, I guess. But I don't want to go too much further actually into that. I don't think I want to graph it. It's more of an algebraic process this time. You don't have to graph things today. Okay. The only other next level, in fact, that's about where I'm going to end the lesson. This is just showing you what you can do with this, okay? This has application in coding, in design, in data management. You can express what I'm going to show you right here with an Excel file, right? Because you can have, okay, my expenses are, on Fridays it's a little more expensive to sell apples for some reason. I want to look at the function for the entire year. So, Friday would be a certain function on how the apples are sold, and I would have to fit that within the schema of the entire year. You see, it's like a box within a box. You ever done that, like a full prank on someone? Their actual gift is really small, and you wrap it all nice. And then what do? You put it in a giant box or in like an iPhone box. So they're all, iPhone, yes. What a good friend. $800. That's not even how much it costs. And then they open the outer box and then, oh crap, there's another inside box. This right here is, the inner gift is h of 2. That is a box inside of g of x. That is a box inside of f of x. It's like a world within a world. But, I could write that whole thing out right here. Or I can just say, well, the innermost room, the innermost present is h of 2. So I would take h, I would do h of 2, plug in 2 here, get a value. You see? That would then be g of whatever that value is. Take the value, plug it in, get a value. That value would be f of what that value is. We would keep building out. That may sound abstract, so let's do it. And I'll do this quickly because this isn't a skill you'll practice today, but you need to see it. H of 2 is equal to 10 times 2 minus 4. That's 20 minus 4, 16. So h of 2 is equal to 16. H of 2 is equal to 16. So guess what's next? G of 16. I solve for h of 2. It's equal to 16. H of 2 right here is just now 16. We got to figure out what G of 16 is, and then we'll be to the outer box. Let's see. So G of 16 is 3 times 16 plus 8, and that's 48 plus 8, 56. G of 16 is 56, and Let this wrap your brain for a second. G of H of 2 is 56. You see the... Okay. If you don't see it, that's okay. It's not for today. It's for expanding a little bit what your scope of these are going to be. Oh, this is going to be horrible. 56 squared plus 1. Obviously, I just picked numbers. All right, so we go 56 squared. We go 56 squared. 31, 36, so we're going to get 31, 37. Because f of x is x squared plus 1. So g of h of x, we just figured out is 56. Now it's f of 56. It's a world within a world within a world. So what? F of g of h of 2 is 3,137. Thumbs up, sideways, down for just that concept. I'm curious. Okay. Some of us, if you didn't get that, how about for the rest of it? How about, no, we'll say first, addition, subtraction, multiplication, thumbs up, sideways, down. We could do that. We've seen it. Okay. How about division? Division? It's around there? Okay, good. That's close. That's close. All right. I have to start getting used to doing that where I think a lot of teachers, well, let's stop this first.